Hello. Okay. Last time we implemented regularization. We got L1 and L2 regularization working, and they both seem to improve our results. We implemented dropout, though I'm not sure if I implemented it properly because it harmed the results slightly. Which is confusing, because I guess I would have expected it either to help slightly or to break it completely. The fact that it harmed it slightly means I may have done it wrong, or maybe I would need to tune the hyperparameters differently in order to get it working. Unfortunately, the book that I'm reading here doesn't cover dropout in detail, so if there was some other tweaks that I would have to do to get it working, it doesn't say what they are, and I don't know what they are. So I'm not sure. I'm not sure what the verdict is on our dropout implementation, but at least we got L1 and L2 working. All right, now we're on to weight initialization. When we create our neural networks, we have to make choices for the initial weights and biases. Up to now, we've been choosing them according to a prescription, which I discussed only briefly back in Chapter 1. Just to remind you, that prescription was to choose both the weights and biases using independent Gaussian random variables. Normalized to have mean 0 and standard deviation 1. While this approach has worked well, it was quite ad hoc, and it's worth revisiting to see if we can find a better way of setting our initial weights and biases, perhaps to help our neural networks learn faster. It turns out we can do quite a bit better than initializing the normalized Gaussians. To see why, suppose we're working with a network with a large number, say 1,000 of input neurons, and let's suppose that we've used normalized Gaussians to initialize the weights connecting to the first hidden layer. For now, I'm going to concentrate specifically on the weights connecting the input neurons to the first neuron in the hidden layer and ignore the rest of the network. Okay, so input layer, everything going into this one first hidden neuron. We'll suppose for simplicity that we're trying to train using a training input X in which half the input neurons are on, i.e. set to 1, and half the input neurons are off, i.e. set to 0. The argument which follows applies more generally, but you'll get the gist of it from this special case. Let's consider the weighted sum Z equals the sum of the products of the weights and the inputs plus the bias of inputs to our hidden neuron. 500 terms in this sum will vanish because the corresponding input xj is 0, and so z is a sum over a total of 501 normalized Gaussian random variables, accounting for the 500 weighted terms and the 1 extra bias term. Thus, z is itself distributed as a Gaussian with mean 0 and standard deviation square root of 501, which is approximately equal to 22.4. That is, z has a very broad Gaussian distribution, not sharply peaked at all. In particular, we can see from this graph that it's quite likely that the absolute value of z will be pretty large, i.e. either z is much greater than 1 or z is much less than -1. If that's the case, then the output sigmoid of z from the hidden neuron will be very close to either 1 or 0. That means our hidden neuron will have saturated, and when that happens, as we know, making small changes to the weights will only make absolutely minuscule changes in the activation of our hidden neuron. That minuscule change in the activation of the hidden neuron will, in turn, barely affect the rest of the neurons in the network at all, and we'll see a correspondingly minuscule change in the cost function. As a result, those weights will only learn very slowly when we use the gradient descent algorithm. Footnote. We discussed this more in detail in Chapter 2. It's similar to the problem we discussed earlier in this chapter, in which output neurons which saturated on the wrong value caused learning to slow down. We addressed that earlier problem with a clever choice of cost function. Unfortunately, while that helped with saturated output neurons, it does nothing at all for the problem with saturated hidden neurons. Oh. I don't think I realized that at the time. So the cost function doesn't have anything to do with the saturation behavior of hidden neurons. Interesting. Okay. I've been talking about the weights input to the first hidden layer. Of course, similar arguments apply also to the later hidden layers. If the weights in the later hidden layers are initialized using using normalized Gaussians, then activations will often be very close to 0, 1, and learning will proceed very slowly. Is there some way we can choose better initializations for the weights and biases so that we don't get this kind of saturation and so avoid a learning slowdown? So here's my guess at this point. Just make the start with smaller weights. If the problem is the weights are too big, start with smaller weights. Suppose we have a neuron with n in input weights. Then we shall initialize those weights as Gaussian random variables with mean 0 and standard deviation 1 over square root of n in. That is, we'll squash the Gaussian down, making it less likely that our neuron will saturate. Okay, we'll continue to choose the bias as a Gaussian with mean 0 and standard deviation 1 for reasons I'll return to in a moment. With these choices, the weighted sum z equals sum of the products of the weights and the inputs plus bias will again be a Gaussian random variable with mean 0, but it'll be much more sharply peaked than it was before. Suppose, as we did earlier, that 500 of the inputs are 0 and 500 are 1, then it's easy to show, see the exercise below, that z has a Gaussian distribution with mean 0 and standard deviation 3 over 2 equals 1.22. This is much more sharply peaked than before, so much so that even the graph below understates the situation. I've had to rescale the vertical axis when compared to the earlier graph. Such a neuron is much less likely to saturate and correspondingly much less likely to have problems with the learning slowdown. Okay, so the trick was to... Is it just to divide... divide by something, but what is it? Maybe I should read the exercise. Exercise: verify that the standard deviation of z equals this. In the paragraph above is square root of 3 over 2. It may help to know that A, the variance of a sum of independent random variables, is the sum of the variances of the individual random variables. And B, the variance is the square of the standard deviation. Okay, I'm a little lost in the math here. I think I have to refresh my understanding of Gaussians and maybe read this a little more carefully. Half the input neurons are on, so we've got half zeros and half ones, and there's 1,000 inputs. The weighted sum X, half of these are 0 and half of them are 1. W's are set according to a Gaussian distribution. Each Gaussian has a mean 0 and a standard deviation 1. And so the sum ends up with a mean 0 and a standard deviation 22.4. Then we're saying, what if you have the standard deviation be square root 1 over square root of n in, so 1 over square root of 1,000. So that's, the mean is the same. The standard deviation is now 3/2. And I think the exercise is to show that it's 3/2. I guess I don't even know where 3/2 came from. It may help to know that the variance of a sum of independent random variables is the sum of the variances. Okay, so the sum of the variances, and that the variance is the square of the standard deviation. So we're saying the standard deviation of each of these is going to be 1/square root of n in, which means the variance is 1/n in. The variance of the sum is going to be equal to the sum of the variances, so that's going to be n in over n in, but then there's also a divided by 2 because only half of them are in the sum, because half of our x's are zeros and half of our x's are ones. So you get, you end up with 1/2 because the n's cancel and you end up with 1/2. Then we take the square root of that to get the standard deviation back, and you get square root of 1/2. So why do they say square root of 3/2? What did I do wrong here? Where could 3 even be coming from? One second. So I don't know where the 3 is coming from. The weights as Gaussian random variables with mean 0 and standard deviation 1/square root of n. So let's just write this. Any particular w is going to have 1/square root of, let's call it n. This is not the variance. This is the standard deviation. We can just call it wj, I guess. Then we're saying z is equal to the sum of wj times xj for j in range 1000 plus b. The standard deviation of B is the same, I think. Oh, actually, did we even talk about what the standard deviation of B is? Maybe that's where the extra thing comes from. Initialize the weights. Okay, so standard deviation of B is still just 1. So for Z, if we want to talk about its standard deviation, that's going to be equal to standard deviation of this whole thing, which is going to be the trick we have is that the standard deviation is the square root of the variance. So square root of variance of these two things. Then the variance of a sum is the sum of the variance. So then we can say variance of U plus variance of U. Variance of B is still 1. Because the standard deviation is still 1. This is the same as this, because half of them are 0 and half of them are 1, so let's just sum over half of them instead. And then the variance of a WJ is going to be n squared, or just n actually. The variance of, is going to be just n. Or like, that's what it was when the weights... Okay, let me just do it step by step. Variance of this is equal to the square of the standard deviation of this, which would mean 1 over n. That's the variance. Then that just means we've got 500. Once you take the sum, it's basically, it's just a half, because it's because you've got 500 on the what am I trying to say? You've got 1 over n is 1,000, 500 times, so that's 1/2. So here's your square root of 3 over 2. Okay, that was tough. That was harder than I thought it would be. All right, I stated above that we'll continue to initialize the biases as before as Gaussian random variables with a mean of 0 and a standard deviation of 1. That is okay, because it doesn't make it too much more likely that our neurons will saturate. In fact, it doesn't much matter how we initialize the biases, provided that we avoid the problem with saturation. Some people go so far as to initialize all the biases to 0 and rely on gradient descent to learn appropriate biases. But since it's unlikely to make much difference, we'll continue with the same initialization procedure as before. Well, why don't we try that? What if we set everything to 0? How does that perform? So if I try right now, I don't remember what, actually, yeah, why don't we move this into the proof? We're doing 100 sigmoids. Let's go back down to 30. To speed it up a bit. So we start with our first one. It basically goes 91, 93 in our first 2 epochs. Now if we change to the network to start with everything at 0, so Just 0. 0 for everything. How well does that do? Is rand n, oh, I guess this is giving a whole matrix. So I could just say zeros, 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 without the random. Does it have an E? No. How do you call zeros? NumPy zeros. Oh, I just need to put this as a tuple instead of as two separate arguments. How does that do? Bad. Really bad. It's not even able to learn. Okay. Versus if it was random. It starts at 91 and then 93, right? 92, 93, 94. Okay. Okay. So zeros doesn't actually work. I don't know why they said like, yeah, you can initialize. Oh, initialize the biases at 0. Well, why don't we try just the biases? Well, it doesn't matter. The biases don't matter that much. The weights are the big thing. So, what is rand n doing? NumPy rand n. Normal distribution. Can I tell it what the mean and standard deviation should be? What are these mystical args? Here, oh, here's the custom mean and standard deviation. Mean is mu. I don't want to change that. Standard deviation is sigma. So you just multiply the matrix. What do you call it? A Hadamard product. So if I just multiply this matrix by 1 over square root of what is n in this case? It's either y or x. What's the issue with this? Square root is not defined. Can I just use a NumPy square root? Is this anything? We're starting at 92.8. So is that a fluke? Because usually we start around 91. $93. Okay, it seems to be starting better than before. $92.4. And then just to see, like, is it possible that x was the right thing to divide by? That's also very good. Very good. Okay, so they're both good, which means I don't know which one's right. And then if I don't divide by anything, which is the same as 1 over 1, does that go back to 91? 92. Huh. 91. Okay. But yeah, I don't know which one it should be. I guess it should be the, when we're talking about the hidden layer, it should be the number of inputs. So it should be the 700 from the layer before. So I think that's why. But I'm not sure. I guess we'll see once we read his code. All right, let's compare the results both for our old and new approaches to weight initialization using the MNIST classification task. As before, we'll use 30 hidden neurons, mini batch size of 10, regularization parameter lambda equals 5.0, and the cross entropy cost function. We will decrease the learning rate slightly from 0.5 to 0.1, since that makes the results a little more easily visible in the graphs. We can train using the old method of weight initialization. We can also train using the new approach of weight initialization. This is actually even easier since Network 2's default way of initializing the weights is using the new approach. That means we can omit the net.largeweight initializer call above. Okay. Old approach, new approach. In both cases, we end up with classification accuracy somewhat over 96%. The final classification accuracy is almost exactly the same in the two cases, but the new weight initialization technique brings us there much, much faster. At the end of the first epoch of training, the old approach to weight initialization has a classification accuracy under 87%, while the new approach is already almost 93%. What appears to be going on is that our new approach to weight initialization starts us off in a much better regime, which lets us get good results much more quickly. Same phenomenon is also seen if we plot the result with 100 hidden neurons. In this case, the two curves don't quite meet. However, my experiments suggest that with just a few more epochs of training not shown, the accuracies become almost exactly the same. So on the basis of these experiments, it looks as though the improved weight initialization only speeds up learning. It doesn't change the final performance on our networks. However, in Chapter 4, we'll see examples of neural networks where the long-run behavior is significantly better with the 1 over square root of n in weight initialization. Thus, it's not only the speed of learning which is improved, it's sometimes the final performance. The 1 over square root of n in approach to weight initialization helps improve the way our neural nets learn. Other techniques for weight initialization have also been proposed, many building on this basic idea. I won't review the other approaches here since 1 over square root of n in works well enough for our purposes. If you're interested in looking further, I recommend looking at the discussion on pages 14 and 15 of a 2012 paper by Yoshua Bengio, as well as the references therein. So actually, they're saying don't worry about the size of the matrix, only use the size of the input. So I shouldn't be doing square root of y, I should be doing square root of sizes of 0. Well, that didn't work. So why does that work worse than Oh, wait, was that just a fluke? 93 point something that time? 93. Okay. Well, this is what it says to do. Does this paper have an easier weight initializing thing? Where is weight initialization? Is that not in here? Weight initialization. Use a combination of the fan in and fan out, e.g. sample a uniform negative R to R with R equals square root of 6 over fan in plus fan out for hyperbolic tangent units, and R equals 4 times square root of 6 over fan in plus fan out for sigmoid units. So that, for us, that would be 4 times square root of 6 divided by x plus y, I believe. No, that doesn't work well at all. Is uniform different than Gaussian? Uniform distribution. Versus Gaussian. Oh. Uniform means literally uniform. So this shouldn't be rand n, it should be random numbers between 0 and 1. NumPy uniform distribution. Random dot uniform. It takes the low and the high. But I can just multiply it by, yeah, I should be able to just do this. Oh, this isn't a shape. So we did rand n before. Is there uniform n? Uniform distribution matrix. You can do size equals. Okay, and that sucks. Even though we're using sigmoids and we're... Oh, wait. I want to be between negative r and r, not between 0 and r. So why don't I say... this is gonna look stupid, but it goes low equals negative this, high equals this. $92. So it didn't even improve it very much. It looks like that improves it a very small amount. Not as much as the other thing we were already doing. It's weird, right? Because we're doing this correctly, aren't we? Recommend scaling by the inverse of the square root of the fan-in, although same authors and the deep learning tutorials use a combination of the fan-in and fan-out, e.g. sample a uniform from negative r to r with this for hyperbolic tangent units, which we're not using, and this for sigmoid units, which we are using. Okay, well, this doesn't seem to work. I mean, it works, but it's not better, so I don't know why you would do it. Versus what seemed to give the best results was rand n, and then you used, you just pass in this, and you multiplied this by 1 over the square root of x. Honestly, is the thing that did the best. I don't know why. So 1 over square root of the fan out is working really well. Though what the book is telling me to do is to use sizes of 0. Actually, that worked really well. I don't know. I guess it is pretty random. I don't know which one is obviously better. All right, so we'll stick with that. Discussion on pages 14 and 15. Is that where we were? Yeah, 15, 14. I guess we could also try setting biases to 0. So that would be zeros, and then you put this as, what's wrong with that? NumPy initialize 0 matrix. Isn't that what I'm doing? Oh, it's not dot random, it's just dot zeros. So if the biases are initialized at 0, that works. It's like, it was better than the last try, but it's, yeah, it kind of doesn't seem to make a difference. Oh, that time it was worse, but I don't know if that, I don't know why. I don't know, it's not noticeably different, so I'll just leave it at 0, because that seems like a good starting point. All right, problem. Connecting regularization and the improved method of weight initialization. L2 regularization sometimes automatically gives us something similar to the new approach to weight initialization. Suppose we are using the old approach to weight initialization. Sketch a heuristic argument that 1. Supposing lambda is not too small, the first epochs of training will be dominated almost entirely by weight decay. 2. Provided eta lambda is much less than n, the weight will decay by a factor of exp of negative eta lambda over m per epoch. And 3. Supposing lambda is not too large, the weight decay will tail off when the weights are down to a size around 1 over square root of n, where n is the total number of weights in the network. Argue that these conditions are all satisfied in the examples graphed in this section. Okay. So I basically understand this. It's saying we have, before today, we were starting our weights really big. L2 regularization penalizes big weights. So then the first few epochs were spent basically undoing our bad initialization and bringing the weights down. So sketch a heuristic argument. That means we don't have to prove it, we just have to hand wave that supposing lambda is not too small, the first epochs of training will be dominated almost entirely by weight decay. Just want to remember lambda. How does it get used again? Okay, so lambda tells you how much to decay weights on each update. So if lambda is not too small, we're going to be decaying weights a lot if the weights start really big. So I think that's our proof of number 1, is that when lambda is big enough, this effect is going to be much bigger than this effect at changing the weights. Then number 2, provided eta times lambda is much less than n. So this is eta times lambda, and it gets divided by n. So if this is very small, the weights will decay by a factor of x of negative eta lambda over m per epoch. Eta lambda much less than n. So this much less than this. Which means you've got a number much smaller than 1 here. A number that's close to 0 here. So you're decaying the weights. I guess I don't really see where this exp and this m are coming from. I think it's because we're like repeatedly doing this scaling. I don't know. And I've said this a few times, but I'm okay with not solving all of the math problems in the book. I'm just trying to I'm trying to build an LLM. That's my goal. So I don't need to know how to invent an LLM. I just need to, or I mean, I don't need to know how to invent it. I just need to figure out how to implement it. So I just want like intuition for this stuff so that it can help me with the implementation. I don't know why specifically it would decay as this exponential. So I think I have to give up on this bullet point number 2. And then supposing lambda is not too large, the weight decay will tail off when the weights are down to a size around 1 over square root of n, where n is the total number of weights in the network. I don't know, honestly. When the weights are down to a size of 1 over square root of n. I don't know. I have to give up on this. I don't know the reason why 1 over square root of n is magic here. The thing I do understand is that at a certain point, the weight decay, the updates are going to stop being dominated by the weight decay once we've trimmed all the fat, and then like the what do you call it? The gradients will start compensating back for the weights that we're losing. But I don't know why 1 over square root of n is the point where that should happen. Yeah, I don't understand this mathematical argument here. Oh well, moving on. Handwriting recognition revisited, the code. Let's implement the ideas we've discussed in this chapter. Done! We'll develop a new program, Network 2, which is an improved version of the program Network.py we developed in Chapter 1. If you haven't looked at Network.py in a while, you may find it helpful to spend a few minutes quickly reading over the earlier discussion. It's only 74 lines of code and is easily understood. As was the case with Network.py, the star of Network2.py is the network class, which we use to represent our neural networks. We initialize an instance of network with a list of sizes for the respective layers of the network and a choice of the cost to use, defaulting to the cross entropy. Yeah, the thing I found is that it doesn't make sense to make cost an argument because it's always going to be the same. The only thing that's going to change, basically you're going to change the cost and the output activation function in tandem. It doesn't make sense to change them independently. So for me, I've just bundled both of those things into output neuron type. Something I wanted to try actually is I had a theory that ReLUs were giving me overflows because my weights were being initialized too large. So now that we've scaled down the weight initialization, does ReLU work? Well, we're not getting overflow errors anymore, but we're still not learning. That's too bad. I really wonder why. Then softmax, is that still working? I mean, maybe it won't work with ReLU. We'll try it and then switch from ReLU. Sigmoid. Oh, that works great. I mean, softmax makes more sense to me than sigmoid with cross entropy for our output. And it seems like it's actually giving better results also. Starting at 94. 93.2, that time was less lucky. But then we jumped to 95 at the second one. Okay, not necessarily better results, but I do like softmax better. Yeah, really confusing why ReLU doesn't work. What about linear? Should linear work? No, there we're getting overflows or something. What is the problem? Invalid value encountered in divide. That's interesting. And it was with the softmax. So what if you do linear and sigmoid cross entropy? Now you get problems. Weird that I'm still, the only combinations I've gotten that work are sigmoid and cross entropy or sigmoid and softmax. Oh. Yeah, it doesn't like the division. Well, I want to try something weird. What if I had 2 layers? Let's try 30-30, sigmoid first. Okay, it works. And then what if I have ReLU before a sigmoid? It's all over the place. It's like, it's actually... It's weirdly all over the place. The idea that I was thinking was ReLU is unbounded, right? Like you can go way higher than 1 as your output. But if I pipe that into a sigmoid first, then it goes back to being bounded between 0 and 1. And so if the problem is that the ReLUs are giving me numbers greater than 1 and softmax doesn't know what to do with that, then maybe putting a sigmoid in between could help. Yeah, I wonder what I'm doing wrong. Does linear work with that trick? So linear into sigmoid into softmax? It has so much trouble learning that I assume something is not working. But then I guess I would also expect linear into a sigmoid with cross entropy should work, and similarly with ReLU, because that avoids the problem I was talking about. Overflow encountered in add. Invalid value. Where's the first error? Overflow encountered in matmul. I wonder why. I don't know. I still don't know. All right, well, we've got our stuff that works. Hopefully we'll find out why the other stuff doesn't work yet. All right, the first couple of lines of the init method are the same as the network.py. The next two lines are new, so weight initializer and cost, and that's not how we're doing it. Let's start by examining the default weight initializer method. This makes use of our new and improved approach to weight initialization. As we've seen in that approach, the weights, I think I might not read through all of this because we've already spent so much time implementing this stuff ourselves. I'm just gonna skip around and see if there's any difference between what he's doing and what I'm doing. So he is dividing by square root of x, which is the thing that I said seemed to work best in practice, but wasn't what I thought he was describing. It's interesting that we came up with the thing that works best empirically. So maybe he will explain why x is n in. Divided by the square root of the number of the connections input to the neuron. Oh, so I just had I had my interpretation of x and y backwards. And he didn't explain what n in was earlier, and I assumed it meant the first layer, but I guess it just means the layer into this neuron. Okay. Import numpy, blah, blah, blah. Large weight initializer, this is what we used to have. We got rid of it because it's never helpful. Can't think of a situation where you'd want to use it. The network's init method is that we initialize a cost attribute. So he's implementing cost and delta. Cost is not actually used. It's only used for graphing. You don't actually need it. You only need the derivative of it. So blah, blah, blah. How to compute the output error. Okay, and then the quadratic cost, which we're basically not using anymore. Although I can use it. The way to use it is to just do sigmoid as the output. Actually, would this go back to doing quadratic cost? I'm actually not sure. Seems to work. Anyway, yeah, the issue is he's not separating the fact that it's a quadratic cost from the fact that it's sigmoids on the output layer. Which is why I've combined those two things together. Okay, we've understood everything. Let's look at the code. Here's the code. All right. I don't think there's anything left that I wanted to understand. The weight initialization was the only thing that I wasn't sure about, and we found the issue with the way we were doing it by reading it. I think the rest of it, I understand. Just read through just to make sure I'm not missing anything. Managed to do the updating mini batches. Oh, I was curious about how they implemented the weight changes with the lambda. So is this, what type of regularization is this using? He doesn't say, but it looks like L2. Yeah. So he is doing it in a different way than, I mean, it's the same thing, but he's using list comprehensions for some reason to do all of the layers at once. And the other weird thing is, well, I guess it's not that weird, but he's not updating the weights in place like I'm doing with the times equals and the minus equals. He's zipping what they used to be with the deltas and then summing those things together, which I think is harder to read, but whatever. But yeah, I don't think I'm learning anything new here. You take what it used to be, you multiply it by 1 minus eta times lambda over n. Multiply it by 1 minus eta times lambda over n. So yeah. And then you don't do that with beta, or with bias, I mean. All right. I don't think this has been changed. This looks about the same. This doesn't really matter to us, saving and loading. I don't know why you'd need to do that. Maybe for really huge networks, it's helpful. One of the more interesting changes in the code is to include L2 regularization. It's so trivial to implement that it might be easy to miss, but yeah, we spotted it. Big impact on results, yes. Another small is several optional flags to monitor the cost into accuracy. Yeah, that doesn't matter to us. That's just how he's drawing his graphs and stuff. Okay. Other additions equals the save method. Yeah, I guess he didn't explain why he wants to have a save and load. Okay, problems. Modify the code above to implement L1 regularization. Done. Can you find a regularization parameter that enables you to do better than running unregularized? Yeah, we did, didn't we? Let's try that one more time. So here's unregularized. Actually, that works pretty well. And then here it is with L1 regularization. That does not work as well. I guess we would have to change lambda. Does a smaller lambda work better? Kinda. Does a really small lambda work better? Kinda. It's actually hard to see the effect of regularization now that we've got the weights initializing better. Because if I set lambda to 0, it still works pretty well. 93, 94, 94. Let's say I set it to be really high, 10. It's so hard to tell if it's helping or hurting. Yeah, it was so much more obvious before we had the weights initialized. What if it's like 500? Can we get it to at least be harmful? Yeah, that's harmful. $50 is harmful. And between 5 and 0, it's like hard to tell if it's doing anything helpful or harmful. Okay, so let's put it back to how it was, L2. I don't know the answer if I can find one that enables me to do better than unregularized. It seems like I can't find one that's obviously better now that the weights are initialized correctly. So I don't know. Take a look at cost derivative method. It was written for the quadratic cost. How would you rewrite the method for cross entropy cost? That was in network.py. In network 2, we've eliminated the cost derivative method entirely, instead incorporating its functionality into the cross entropy cost.delta method. So I guess I have to find the old implementation and see what was wrong with it. Cost derivative. Which was output activations minus y, which is kind of still how it works. Because the delta is just doing the same thing, right? It's still just a minus y. So what's the problem that it's expecting me to identify? Oops, did I go too far? Yeah. Right. I've lost the plot. Where was this problem? Here. How would you rewrite the method for the cross entropy cost? Cost derivative. So it's output minus y, and then you multiply that by a sigmoid prime, right? Delta, yeah, you're multiplying it by a sigmoid prime. And the issue is you don't want to multiply it by a sigmoid prime when you're using cross entropy. So I think what he's saying is you have to make the whole delta be a function, because you can't, because the cost derivative is always a minus y, but you have to either multiply it by sigmoid prime or not, depending on what the cost function is. I think that's what they're trying to say. So yeah. All right. All right, let's move on. How to choose a neural network's hyperparameters. Up until now, I haven't explained how I've been choosing values for the hyperparameters, such as the learning rate eta, the regularization parameter lambda, and so on. I've just been supplying values which work pretty well. In practice, when you're using neural nets to attack a problem, it can be difficult to find good hyperparameters. Imagine, for example, that we've just been introduced to the MNIST problem and have begun working on it, knowing nothing at all about what hyperparameters to use. Let's suppose that by good fortune, in our first experiments, we choose many of the hyperparameters in the same way as was done earlier in this chapter. 30 hidden neurons, mini batch size of 10, training for 30 epochs using cross entropy, but we choose a learning rate eta equals 10.0 and regularization parameter lambda equals 1000. Here's what I saw on one such run. So you never learn. Our classification accuracies are no better than chance. Our network is acting as a random noise generator. Well, that's easy to fix, you might say. Just decrease the learning rate and regularization hyperparameters. Unfortunately, you don't a priori know these are the hyperparameters you need to adjust. Maybe the real problem is that our 30 hidden neuron network will never work well, no matter how the other hyperparameters are chosen. Maybe we really need at least 100 hidden neurons, or 300 hidden neurons, or multiple hidden layers, or a different approach to encoding the output. Maybe our network is learning, but we need to train for more epochs. Maybe the mini batches are too small. Maybe we do better by switching to the quadratic cost function. Maybe we need to try a different approach to weight initialization, and so on and so on. It's easy to feel lost in hyperparameter space. This can be particularly frustrating if your network is very large or uses a lot of training data, since you may train for hours or days or weeks only to get no results. If the situation persists, it damages your confidence. Maybe neural networks are the wrong approach to your problem. Maybe you should quit your job and take up beekeeping. That's a little extreme. In this section, I explain some heuristics which can be used to set the hyperparameters in a neural network. The goal is to help you develop a workflow that enables you to do a pretty good job of setting hyperparameters. Of course, I won't cover everything about hyperparameter optimization. That's a huge subject, and it's not in any case a problem that is ever completely solved, nor is there universal agreement amongst practitioners on the right strategies to use. There's always one more trick you can try to eke out a bit more performance from your network, but the heuristics in this section should get you started. Broad strategy. When using neural networks to attack a new problem, the first challenge is to get any non-trivial learning, i.e. for the network to achieve results better than chance. This can be surprisingly difficult, especially when confronting a new class of problem. Let's look at some strategies you can use if you're having this kind of trouble. Suppose, for example, that you're attacking MNIST for the first time. You start out enthusiastic, but are a little discouraged when your first network fails completely, as in the above example. The way to go is to strip the problem down. Get rid of all the training and validation images, except images which are zeros or ones, then try to train a network to distinguish zeros from ones. Not only is that an inherently easier problem than distinguishing all 10 digits, it also reduces the amount of training data by 80%, speeding up training by a factor of 5. That enables much more rapid experimentation, and so it gives you more rapid insight into how to build a good network. You can further speed up your experimentation by stripping your network down to the simplest network that likely to do meaningful learning. If you believe a 784,10 network can likely do better than chance classification of MNIST digits, then begin your experimentation with such a network. It'll be much faster than training a 784,30,10 network, and you can build back up to the latter. You can get another speed up in experimentation by increasing the frequency of monitoring. In network.py, we monitor the performance at the end of each training epoch. With 50,000 images per epoch, that means waiting a little while, about 10 seconds per epoch on my laptop. When training a 784,30,10 network before getting any feedback on how well the network is learning. Of course, 10 seconds isn't very long, but if you want to trial dozens of hyperparameter choices, it's annoying. And if you want to trial hundreds of thousands of choices, it starts getting debilitating. We can get feedback more quickly by monitoring the validation accuracy more often, say after every 1,000 training images. Furthermore, instead of using the full 10,000 image validation set to monitor performance, we can get a much faster estimate using just 100 validation images. All that matters is that the network sees enough images to do real learning and to get a pretty good rough estimate of performance. Of course, our program network2.py doesn't currently do this kind of monitoring, but as a pledge to achieve a similar effect for the purposes of illustration, we'll strip down our training data to just the first 1,000 MNIST training images. Let's try it and see what happens. To keep the code below simple, I haven't implemented the idea of using only 0 and 1 images. Of course, that can be done with just a little more work. Okay, so you just take the first 1,000. But you have bad hyperparameters, so it still doesn't learn. We're still getting pure noise, but there's a big win. We're now getting feedback in a fraction of a second rather than once every 10 seconds or so. That means you can more quickly experiment with other choices of hyperparameters, or even conduct experiments trialing many different choices of hyperparameters nearly simultaneously. In the above example, I left lambda as lambda equals 1,000, but as we used earlier, but since we changed the number of training examples, we should really change lambda to keep the weight decay the same. That means changing lambda to 20. If we do that, then this is what happens. Oh, we start to learn. That's why it's weird that lambda is defined as a number instead of, or is not defined as a ratio. What am I trying to say? It's weird that the definition of lambda doesn't already divide by n. I don't get that. Anyway. Aha, we have a signal. Not a terribly good signal, but a signal nonetheless. That's something we can build on, modifying the hyperparameters to get further improvement. Maybe we can guess that our learning rate needs to be higher. As you perhaps realize, that's a silly guess for reasons we'll discuss shortly, but please bear with me. So to test our guess, we tried dialing eta up to 100. And then it stopped learning. That's no good. It suggests that our guess was wrong, and the problem wasn't that the learning rate was too low. Instead, we tried dialing eta down to 1, and that helped. That's better. We can continue individually adjusting each hyperparameter, gradually improving performance. Once we've explored to find an improvement value for eta, then we can move on to find a good value for lambda, then experiment with a more complex architecture, say a network with 10 hidden neurons, then adjust the values for eta and lambda again, then increase to 20 hidden neurons, then adjust the hyperparameters some more, and so on. At each stage, evaluating performance using our held out validation data, and using those evaluations to find better and better hyperparameters. As we do so, it typically takes longer to witness the impact due to modifications of the hyperparameters, and so we gradually decrease the frequency of monitoring. This all looks very promising as a broad strategy. However, I want to return to that initial stage of finding hyperparameters that enable the network to learn anything at all. In fact, even the above discussion conveys too positive an outlook. It can be immensely frustrating to work with a network that's learning nothing. You can tweak hyperparameters for days and still get no meaningful response. And so I'd like to re-emphasize that during the early stages, you should make sure you can get quick feedback from experiments. Intuitively, it may seem as though simplifying the problem and the architecture will merely slow you down. In fact, it speeds things up, since you much more quickly find a network with a meaningful signal. Once you've got such a signal, you can often get rapid improvements by tweaking the hyperparameters. As with many things in life, getting started can be the hardest thing to do. Okay, that's the broad strategy. Let's now look at some specific recommendations for setting hyperparameters. I will focus on the learning rate, eta, the L2 regularization parameter, lambda, and the mini batch size. However, many of the remarks also apply to other hyperparameters, including those associated to network architecture, other forms of regularization, and some hyperparameters we'll meet later in the book, such as the momentum coefficient. Learning rate. Suppose we run 3 MNIST networks with 3 different learning rates. Eta equals 0.025, eta equals 0.25, and eta equals 2.5 respectively. We'll see the other hyperparameters as for the experiments in earlier sections. Running over 30 epochs with a mini batch size of 10 and with lambda equals 5.0, we'll also return to using the full 50,000 training images. Here's a graph showing the behavior of the training cost as we trained. Footnote, the graph was generated by multiple eta.py. So the middle eta seemed to be the best. With eta equals 0.025, the cost decreases smoothly until the final epoch. With eta equals 0.25, the cost initially decreases, but after about 20 epochs it is near saturation, and therefore most of the changes are merely small and apparent random oscillations. Finally, with eta equals 2.5, the cost makes large oscillations right from the start. To understand the reason for the oscillations, recall that stochastic gradient descent is supposed to step us gradually down into a valley of the cost function. However, if eta is too large, then its steps will be so large that they may actually overshoot the minimum, causing the algorithm to climb up out of the valley instead. That's likely what's causing the cost to oscillate when eta equals 2.5. Footnote. The picture is helpful. Okay. This picture is helpful, but it's intended as an intuition-building illustration of what may go on, not as a complete exhaustive explanation. Briefly, a more complete explanation is as follows. Gradient descent uses a first-order approximation to the cost function as a guide to how to decrease the cost. For large eta, higher-order terms in the cost function become more important and may dominate the behavior, causing gradient descent to break down. This is especially likely as we approach minima and quasi-minima of the cost function, since near such points the gradient becomes small, making it easier for higher order terms to dominate the behavior. When we choose eta equals 0.25, the initial steps do take us towards a minimum of the cost function. And it's only once we get near that minimum that we start to suffer from the overshooting problem. And when we choose eta equals 0.025, we don't suffer from this problem at all during the first 30 epochs. Of course, choosing eta so small creates another problem, namely that it slows down stochastic gradient descent. An even better approach would be to start with eta equals 0.25, train for 20 epochs, and then switch to 0.025. We'll discuss such variable learning rate schedules later. For now though, let's stick to figuring out how to find a single good value for the learning rate eta. With this picture in mind, we can set eta as follows. First, we estimate the threshold value for eta at which the cost of the training data immediately begins decreasing, instead of oscillating or increasing. This estimate doesn't need to be too accurate. You can estimate the order of magnitude by starting with eta equals 0.01. If the cost decreases during the first few epochs, then you should successively try eta equals 0.1, 1.0, etc. until you find a good value for eta. Find a value for eta where the cost oscillates or increases during the first few epochs. Alternatively, if the cost oscillates or increases during the first few epochs where eta equals 0.01, then try 0.001, 0.0001, etc. until you find a good value for eta where the cost decreases during the first few epochs. Following this procedure will give us an order of magnitude estimate for the threshold value of eta. You may optionally refine your estimate to pick out the largest value of eta at which the cost decreases during the first few epochs, say eta equals 0.5 or eta equals 0.2. There's no need for this to be super accurate. This gives us an estimate of the threshold value of eta. Obviously, the actual value of eta that you use should be no larger than the threshold value. In fact, if the value of eta is to remain usable over many epochs, then you likely want to use a value for eta that is smaller, say a factor of 2 below the threshold. Such a choice will typically allow you to train for many epochs without causing too much of a slowdown in learning. In the case of the MNIST data, following this strategy leads to an estimate of 0.1 for the order of magnitude for the threshold value of eta. After some more refinement, we obtain the threshold value eta equals 0.5. Following the prescription above, this suggests using eta equals 0.25 as our value for the learning rate. In fact, I found that using eta equals 0.5 worked well enough over 30 epochs that for the most part I didn't worry about using a lower value of eta. This all seems quite straightforward. However, using the training cost to pick eta appears to contradict what I said earlier in this section, namely that we pick hyperparameters by evaluating the performance using our held out validation data. In fact, we'll use validation accuracy to pick the regularization hyperparameter, the mini batch size, and learning parameters such as the number of hidden layers of neurons, and so on. Why do things differently for the learning rate? Frankly, this choice is my personal aesthetic preference and is perhaps somewhat idiosyncratic. The reasoning is that the other hyperparameters are intended to improve the final classification accuracy on the test set, and so it makes sense to select them on the basis of validation accuracy. However, the learning rate is only incidentally meant to impact the final classification accuracy. Its primary purpose is really to control the step size and gradient descent and monitoring the training cost is the best way to detect if the step size is too big. With that said, this is a personal aesthetic preference. Early on during learning, the training cost usually only decreases if the validation accuracy improves, and so in practice it's unlikely to make much difference which criterion you use. Use early stopping to determine the number of training epochs. As we discussed earlier in the chapter, early stopping means that at the end of each epoch, we should compute the classification accuracy on the validation data. When that stops improving, terminate. This makes setting the number of epochs very simple. In particular, it means that we don't need to worry about explicitly figuring out how the number of epochs depends on the other hyperparameters. Instead, that's taken care of automatically. Furthermore, early stopping also automatically prevents us from overfitting. This is of course a good thing, although in the early stages of experimentation it can be helpful to turn off early stopping so you can see any signs of overfitting and use it to inform your approach to regularization. Okay, we actually implemented early stopping already, but it wasn't very good, and so we've got it commented out. To implement early stopping, we need to say more precisely what it means that the classification accuracy has stopped improving. As we've seen, the accuracy can jump around quite a bit, even when the overall trend is to improve. If we stop the first time the accuracy decreases, then we'll almost certainly stop when there are more improvements to be had. A better rule is to terminate if the best classification accuracy doesn't improve for quite some time. Suppose, for example, that we're doing MNIST, then we might elect to terminate if the classification accuracy hasn't improved during the last 10 epochs. This ensures that we don't stop too soon in response to bad luck in training, but also that we're not waiting around forever for an improvement that never comes. No improvement in 10 is close to what I ended up doing. My rule was, if I'm not better than the median of the last 10 validations, then stop. I don't know what no improvement in 10 means exactly. I guess it should mean my current value is worse than the last 10. No, it shouldn't mean that. It should mean that I don't know. This no improvement in 10 rule is good for initial exploration of MNIST. However, networks can sometimes plateau near a particular classification accuracy for quite some time, only then to begin improving again. If you're trying to get really good performance, the no improvement in 10 rule may be too aggressive about stopping. In that case, I can suggest using the no improvement in 10 rule for initial experimentation and gradually adopting more lenient rules as you better understand the way your networks train, your network trains. The no improvement in 20, no improvement in 50, and so on. Of course, this introduces a new hyperparameter to optimize. In practice, however, it's usually easy to set this hyperparameter to get pretty good results. Similarly, for problems other than MNIST, the no improvement in 10 rule may be much too aggressive or not nearly aggressive enough depending on the details of the problem. However, with a little experimentation, it's usually easy to find a pretty good strategy for early stopping. We haven't used early stopping in our MNIST experiments to date. The reason is that we've been doing a lot of comparisons between different approaches to learning. For such comparisons, it's helpful to use the same number of epochs in each case. However, it's well worth modifying network 2.py to implement early stopping. Modify network 2.py so that it implements early stopping using a no improvement in n epoch strategy where n is a parameter that can be set. Well, okay, what does it mean that there's been no improvement in 10? Does it mean that the best that I've ever done is not inside my last 10? Maybe that's what it should mean. Best ever equals float. If validation is greater than best ever, or just best ever equals max of best ever and validation. It doesn't equal float. It is a float. It's equal to 0. So don't look at the mean, just check if best ever in last 10. Let's just call it last 10. We don't need to keep repeating validation. And if we want to solve the problem correctly, or yeah, the thing the problem says, it needs to be last n. We'll just call it recent. I don't really want to pass this as a parameter, but this is what it is. If you're not in recent, you do this. No improvement in 10. Okay. Does it work? Let's see. I guess here, to give it a chance, go for 300 epochs. Can you think of a rule for early stopping other than no improvement in n? Ideally, the rule should compromise between getting high validation accuracies and not training too long. Add your rule to network.py and run 3 experiments comparing the validation accuracies and number of epochs of training to no improvement in 10. let's think of one. I don't know if I care to implement it, but like the mean thing is an example. It's not a good rule though. You could do something like check if your how do I say this? Like check if your cost is still going down, for example. So you could do some calculations on the cost instead of on the validation. Yeah, I don't know. There's a bunch of stuff you could do. But they're all kind of the same thing. They're like, once you stopped learning, you stop training. It's wild that this hasn't halted yet. I would think that our max hasn't always been in the last 10. $95.76, that's pretty high. So once that goes out of, well, yeah. We should have stopped by now because the last 10 don't include 95.76. So what am I doing wrong? I know what I'm doing wrong. I'm not using early stopping. Stopping equals early. Let's try that again. Learning rate schedule. We've been holding the learning rate eta constant. However, it's often advantageous to vary the learning rate. Early on during the learning process, it's likely that the weights are badly wrong, and so it's best to use a large learning rate that causes the weights to change quickly. Later, we can reduce the learning rate as we make more fine-tuned adjustments to our weights. There we go, we stopped. How should we set the learning rate schedule? Many approaches are possible. One natural approach is to use the same basic idea as early stopping. The idea is to hold the learning rate constant until the validation accuracy starts to get worse. Then decrease the learning rate by some amount, say by a factor of 2 or 10. We repeat this many times until, say, the learning rate is a factor of 1,000 times lower than the initial value. Then we terminate. A variable learning schedule can improve performance, but it also opens up a world of possible choices for the learning schedule. These choices can be a headache. You can spend forever trying to optimize your learning schedule. For first experiments, my suggestion is to use a single constant value for the learning rate. That'll get you a good fixed first approximation. Later, if you want to obtain the best performance from your network, it's worth describing with a learning schedule along the lines I've described. Footnote, a readable recent paper which demonstrates the benefits of variable learning rates in attacking MNIST is this thing. Modify network2.py so that it implements a learning schedule that halves the learning rate each time the validation accuracy satisfies the no improvement in 10 rule, and terminates when the learning rate has dropped to 1/128th of its original value. Okay. Got to figure out a good way to do this. I've been meaning to come back in here and fix the code so that it's not so crazy. And like I can pass parameters in better. Like, how can I pass a learning schedule in? Well, where does, okay, Ada goes into update mini batch. So basically, I'd have to add something like learning schedule. Hold on. Learning. This is obviously not where I want to save this. Learning.py or schedule.py. Maybe just learning schedule.py. Learning schedule is a class that's going to have two methods. Well, first it needs to start with a starting point. Ada equals, Ada is a float. Ada equals Ada. It's going to have a few methods. So one method for when it's time to decrease. This is so weird to try to write like this. One method's for when it's time to stop. Though that's not necessarily the learning rate's responsibility, so maybe I'll omit that. So maybe actually there's only one method and it's update. Change the learning rate if needed. So then instead of Ada, you would be allowed to pass in a learning schedule. What was my Ada a second ago? 1.0. Maybe it should be 5.0. So from learning schedule, import learning schedule. We'll export learning schedule. This isn't enforced by Python, but it's enforced by certain tools like TAC. And then the idea for network is Ada is either a float or a learning schedule. Let's just say it's always a learning schedule, which means you need to import it. From learning schedule, import learning schedule. Which means we'll just call this learning schedule. We'll hit this with at eta equals learning schedule.eta, which means this should still work even though learning schedule doesn't do anything right now. Pass for now. Okay, it still works. Yeah, 5 is too high. 1 is fine. Okay, so that still works because we're just using this as a container for our eta. So now if we go here, the idea is to pass in the learning schedule there, and then have the learning schedule get updated as we go. So learning schedule dot update, which will let it change its own eta. But we need to give it enough information to know what it's supposed to be doing. So what information would that need to be? It needs to be the validation. Here's where there's some entanglement between the different things. Like, what if I don't have validation? Then I guess the learning, I either should throw an exception that says, hey, you can't have a learning schedule if you're not validating, or I would just never vary my learning rate. Anyway, early stopping has not actually been very helpful, so I'm going to comment it out. This stuff that it's doing, though, is now going to be repurposed inside the learning schedule. So we want to keep track of self.recent. So list of floats. Self.best is a float. I don't know how we validate. Maybe we'll take that as an input. And this doesn't return anything. Neither does this. So here we might need to pass in validation. Validation equals self.validate validation data. If validation data. Okay, you don't need to remember the recent and the best ever. I'm just gonna get rid of the stopping criteria. I don't think it's helpful right now compared to the learning schedule. Okay, so you just take validation as input. You've got self.recent to remember them across time. You've got self.best, self.best, self.recent, self.best. I'm not going to do the terminates thing. I'm just going to have it keep running, and we can stop it ourselves. Well, what I can do is if self.ada, we could remember the starting ada. Is less than self.starting over 128. Then whatever. Like that's when we can terminate. We're not learning anymore. Okay. Does this work? You know what would be helpful is if I were printing ada. So once we're done learning, so once our best is not in the last 10, we should have ada and keep going. There it went. We just did. We did it again. Did it again. Okay, and we did it again. I forgot to... Oh, actually, we did it twice in a row. Interesting. I guess we don't reset the count once... once we go once. Another twice in a row there. And we're going to keep getting smaller and smaller and smaller and smaller because I didn't actually implement the stopping point. But there it is. I think that satisfies what I was trying to do. Okay. Well, we should probably keep ada there. Just to not forget that we're doing wacky stuff. Actually, here's another thing to do. Learning schedule. Oops. Copy this. There's a few versions of this that I want. So I want something just called learning schedule. Trying to remember, how does protocol work? Python protocol. Use subclass protocol. Okay, so learning schedule is a protocol. That looks like this. Let's call this decay learning. And then let's have one called constant, or decay schedule, constant schedule. So what does constant schedule do? It never updates. Then here I can just pass in a constant schedule. I don't need learning schedule. I should import decay schedule, and I should add no QA here. Okay, so now it should never change. This is the same as just saying eta equals 1, like we were doing before. And I should export the other two types of things here. Decay schedule. And constant schedule. Cool. How's the constant schedule doing? Yep, it's remaining constant. Good. Okay. Regularization parameter, lambda. I suggest starting initially with no regularization, lambda equals 0.0, and determining a value for eta as above. Using the choice of eta, we can then use validation data to select a good value for lambda. Start by trialing lambda equals 1.0 and then increasing or decreasing by factors of 10 as needed to improve performance on the validation data. Once you've found a good order of magnitude, you can fine-tune your value of lambda. That said, you should return you should return and re-optimize the learning rate again. I don't have a good principle justification for using this as a starting value. Okay. Exercise. It's tempting to use gradient descent to try to learn good values for hyperparameters such as lambda and eta. Can you think of an obstacle to using gradient descent to determine lambda? Can you think of an obstacle to using gradient descent to determine eta? Well, it wasn't tempting me to use gradient descent, but the obstacle is lambda and eta need to be part of your cost function in order to do gradient descent. So you'd have to come up with a cost function that's like okay, let me say this a better way. Lambda and eta don't impact the cost. They only impact how the cost changes over time. They impact what changes you're going to make to your weights, but they don't impact the cost once the weights are chosen. So you need a cost function to do gradient descent. The cost function would have to be something like how far away is, it's basically like my network is learning this fast. How far away is that from my target rate of learning? Because that's the things that lambda and eta control, is the rate of learning. But you can't do that because the rate of learning is not a mathematical function. It's like an empirical fact of like what you see when you run the neural networks, or like when you perform gradient descent. So that's my answer for that. How I selected hyperparameters earlier in this book. If you use the recommendations in this section, you'll find, well, okay, it didn't ask us to implement the lambda searching code. I guess I'm not super happy with how lambda is a function of train here instead of something else that's hard for me to describe. Like I want to do something like learning schedule, but for regularization. So let's do that. Obviously don't put it there. Regularization.py. From typing import protocol class regularization implements protocol. What does it have? It has an init. Actually, it doesn't need to have an init. That doesn't need to be part of its signature. I should say that that's the same. Does this need an init? No. The only thing it needs is this. Okay, regularization. It's a thing that updates weights. So I want to call it like self.regularization. On my weights. Self.regularization.regularize on my weights. So you're going to have a method called regularize that takes a NumPy array. So import NumPy as NP. np.ndArray is what they're called when they're in a type. And it doesn't return anything. It just modifies the weights in place. Weights. Okay. Then we've got a few examples We've got L1 regularization. We've got L2 regularization. And we've got no regularization. So this one's the easiest. You just don't do anything. And I think that means I can... Oh, okay. I also want these to take a lambda. Lambda is a float. Self.lambda equals lambda. L1 and L2 both need a lambda. No regularization doesn't. Network, you've got to take regularization here. So we don't need stopping anymore. We don't need lambda in this way anymore. We just want regularization is a regularization. It can even have a default, which is equal to no regularization. Expression of type no regularization cannot be assigned. Oh, because I need to initialize it. This is an odd thing to do. In Python, because this thing is going to be shared between all calls of this method. In this case, that's okay because it doesn't do anything anyway. Okay, so update mini batch is not going to take lambda anymore. Oh, I said self.regularization. I think instead I have to pass the regularization down, which is annoying. So you're not doing self.regularization. You've taken the regularization from your parent. So you don't get lambda, you get regularization. Okay. So let's go find L2. This is what it looks like. All right, so lambda is going to be self.lambda. Eta and n, I don't know. So let's take them as parameters. Eta float, n float. Regularize weights, eta, n. What's the problem with this? Oh, I guess, Ada and which means we need to do the same here and the same here. This would be L1. Now, now I need to figure out if arrays are passed by reference or by value. I'm guessing this will work. I think this will work. I think this modifies it in place. NumPy modify array in place. We can test it actually. Let's just open Python, import NumPy as np. A is equal to np.array123. Let's do def func. It takes an argument called b. That's an np.nd array. That does b plus equals 1. And call func on A, and then print A. Call func on A again. Okay, so it does modify them in place the way we want. So this should be working pretty much. Instead of passing lambda, now I pass regularization equals L2 regularization. And what was the parameter? What was, I was doing 5.0. So 5.0. It didn't crash, which means it's probably working. Right? I think it's probably working. I'm surprised it didn't crash though, because I changed a lot of stuff. I don't love that I have to pass Ada and N down, especially N. That seems really weird. Because N is getting passed down from really far away. So N is the length of the training data, which is something that the regularization needs and nothing else needs. So I think that's telling me that I want to put it in here. N equals len of data dot training. L2 regularization. Don't take n as input. But take it as input in your thing here if you need it. N is a float. Self.n equals n. N is a float. Self.n equals n. Which will mean this should work now. In network, we don't need to pass n down here anymore. We don't need you anymore. You don't need that anymore. Still work? Still works. So now we can switch between L1 regularization, L2 regularization. Oops. Let's add a no QA here because I want to be able to import stuff even if I don't use it. L1, does that work? Yep. No regularization. So this should use the default parameter, which is no regular, or it's in here, no regularization. Nice. Okay. Yeah, let's use L2 because that works the best. All right. Where were we? Oh, searching for the regularization rate, lambda. So I can do lambda equals this and eta equals this, just so that the word is there and it's readable. I don't think I'm gonna do that. I guess you probably could at this point. You would just add a method to regularization that's like update. I kind of think it's weird to do that inside the training, and that should be something that lives outside the training, something to find the hyperparameters. The learning schedule makes sense inside training because that's not really a hyperparameter. Or I mean, it is a hyperparameter, but you're not searching for a hyperparameter. You know what I mean? Because it's like the learning schedule is a hyperparameter. Whereas the regularization schedule is not a hyperparameter. It's just lambda that's the hyperparameter. You wouldn't want to vary lambda during the training, but you would want to vary eta during the training. So I think finding a good lambda is something that should not be part of the training. All right, how I selected the hyperparameters earlier in this book. If you use the recommendations in this section, you'll find that you get values for eta and lambda, which don't always exactly match the values I've used earlier in the book. The reason is that the book has narrative constraints that have sometimes made it impractical to optimize the hyperparameters. Think of all the comparisons we've made to different approaches to learning, e.g. comparing the quadratic and entropy cost functions, comparing the old and new methods to weight initialization, running with and without regularization, and so on. To make such comparisons meaningful, I've usually tried to keep hyperparameters constant across the approaches being compared, or to scale them in the appropriate way. Of course, there's no reason for the same hyperparameters to be optimal for all the different approaches to learning, so the hyperparameters I've used are something of a compromise. As an alternative to this compromise, I could have tried to optimize the heck out of the hyperparameters for every single approach to learning. In principle, that'd be better, fairer approach, since we'd then see the best from every approach to learning. However, we've made dozens of comparisons along these lines, and in practice have found it too computationally expensive. That's why I've adopted the compromise of using pretty good but not necessarily optimal choices for the hyperparameters. Mini batch size. How should we set the mini batch size? To answer this question, let's first suppose that we're doing online learning, i.e. that we're using a mini batch size of 1. The obvious worry about online learning is that using mini batches which contain just a single training example will cause significant errors in our estimate of the gradient. In fact, though the errors turn out to not be such a problem. The reason is that the individual gradient estimates don't need to be super accurate. All we need is an estimate accurate enough that our cost function tends to keep decreasing. It's as though you're trying to get to the north magnetic pole, but have a wonky compass that's 10 to 20 degrees off each time you look at it. Provided you stop to check the compass frequently, and the compass gets the direction right on average, you'll end up at the north magnetic pole just fine. Based on this argument, it sounds as though we should use online learning. In fact, the situation turns out to be more complicated than that. In a problem in the last chapter, I pointed out that it's possible to use matrix techniques to compute the gradient update for all examples in a mini batch simultaneously, rather than looping over them. And that's what I've got implemented. That's this craziness over here. X equals H stack. Pretty cool. Depending on the details of your hardware and linear algebra library, this can make it quite a bit faster to compute the gradient estimate for a mini batch size of, for example, 100, rather than computing the mini batch gradient estimate by looping over the 100 training examples separately. It might take, say, only 50 times as long rather than 100 times as long. Now at first, it seems as though this doesn't help us much. With our mini batch size of 100, the learning rate for the weights looks like W goes to W prime equals W minus eta over 100 times the sum of the gradients of the cost functions over the examples, where the sum is over training examples in the mini batch. This is versus W goes to W prime equals W minus eta times gradient of the cost function with respect to, or the cost function, the gradient of the cost function on an example, X being one example, for online learning. Even if it only takes 50 times as long to do the mini batch update, it still seems likely to be better to do online learning. However, because we'd be updating so much more frequently. Suppose, however, that in the mini batch case, we increase the learning rate by a factor of 100. So the update rule becomes, you don't have the divided by 100 for the average, you just have the same as before without the divided by 100. That's a lot like doing 100 separate instances of online learning with a learning rate of eta, but it only takes 50 times as long as doing a single instance of online learning. Of course, it's not truly the same as 100 instances of online learning, since in the mini batch, the gradients of the cost functions are all evaluated for the same set of weights as opposed to the cumulative learning that occurs in the online case. Still, it seems distinctly possible that using the larger mini batch would speed things up. With these factors in mind, choosing the best mini batch size is a compromise. Too small, and you don't get to take full advantage of the benefits of good matrix libraries optimized for fast hardware. Too large, and you're simply not updating your weights often enough. What you need is to choose a compromise value which maximizes the speed of learning. Fortunately, the choice of mini batch size at which the speed is maximized is relatively independent of the other hyperparameters, apart from overall architecture. So you don't need to have optimized those hyperparameters in order to find good mini batch size. The way to go, therefore, is to use some acceptable but not necessarily optimal values for other hyperparameters, and then trial a number of different mini batch sizes, scaling eta as above. Plot the validation accuracy versus time, as in real elapsed time, not epoch, and choose whichever mini batch size gives you the most rapid improvement in performance. With the mini batch size chosen, you can then proceed to optimize the other hyperparameters. Of course, as you've no doubt realized, I haven't done this optimization in our work. Indeed, our implementation doesn't use the faster approach to mini batch updates at all. Mine does. I've simply used a mini batch size of 10 without comment or explanation in nearly all examples. Because of this, we could have sped up learning by reducing the mini batch size. I haven't done this in part because I wanted to illustrate the use of mini batches beyond size 1, and in part because my preliminary experiments suggested that the speed up would be rather modest. In practical implementations, however, we would most certainly implement the faster approach to mini batch updates and then make an effort to optimize the mini batch size in order to maximize our overall speed. So, what mini batch size works best for me? I haven't tried varying it. What if it's 100 instead of 10? We've been doing about 1 epoch per second. So this is 1.2 epochs per second, but in theory, the learning is slower now. How about 50? That's the same speed up, 1.2 per second. In theory, the learning is not as bad as it was with 100. But, like, I don't know. 20. The actual speed of this percentage increase is hard for me to estimate. It's too small of differences. So I guess because of that, why not do something that has faster epoch sizes? If I can't tell the difference anyway, might as well be faster, because that I can see that it's faster. Also want to go back to 30 epochs so that it actually ends within a minute instead of within forever. Automated techniques. I've been describing these heuristics as though you're optimizing your hyperparameters by hand. Hand optimization is a good way to build up a feel for how neural networks behave. However, and unsurprisingly, a great deal of work has been done on automating the process. A common technique is grid search, which systematically searches through a grid in hyperparameter space. A review of both the achievements and limitations of grid search, which systematically searches of grid search with suggestions from easily implemented alternatives, may be found in a 2012 paper by James Bergstra and Yoshua Bengio. Many more sophisticated approaches have also been proposed. I won't review all that work here, but do want to mention a particularly promising 2012 paper which used a Bayesian approach to automatically optimize hyperparameters. The code for the paper is publicly available and has been used with some success by other researchers. That's pretty old now, so I wonder, like, what's the state of the art for optimizing neural network hyperparameters? State of the art. Is this a good way to search for this kind of thing? Alright, get out of here. Just tell me. HPO strategies. What if I just look up optimize hyperparameters PyTorch? Is there just a thing that does it? RayTune? RayTune is an industry standard tool. And how does it do it? Grid search. Okay, interesting. Good to know. Summing up, following the rules of thumb I've described won't give you the absolute best possible results from your neural network, but it will likely give you a good start and a basis for further improvements. In particular, I've discussed the hyperparameters largely independently. In practice, there are relationships between the hyperparameters. You may experiment with Ada, feel that you've got it just right, then start to optimize for lambda, only to find that it's messing up your optimization for Ada. In practice, it helps to bounce backward and forwards, gradually closing in good values. Above all, keep in mind that the heuristics I've described are rules of thumb, not rules cast in stone. You should be on the lookout for signs that things aren't working, and be willing to experiment. In particular, this means carefully monitoring your network's behavior, especially the validation accuracy. The difficulty of choosing hyperparameters is exacerbated by the fact that the lore about how to choose hyperparameters is widely spread across many research papers and software programs, and often is only available inside the heads of individual practitioners. There are many papers setting out sometimes contradictory recommendations for how to proceed. However, there are still a few particularly useful papers that synthesize and distill out much of this lore. Yoshua Bengio has a 2012 paper that gives some practical recommendations for using backpropagation and gradient descent to train neural networks. We took a look at that paper earlier already. Including deep neural nets, Bengio discusses many issues in much more detail than I have, including how to do a more systematic hyperparameter searches. Another good paper is a 1998 paper by Yann LeCun, Lian Botu, Geneviève Orr, and Klaus Robert Muller. Though these papers appear in an extremely useful 2012 book that collects many tricks commonly used in neural networks. The book is called Neural Networks Tricks of the Trade. The book is expensive, but many of the articles have been placed online by their respective authors with what presumes the blessing of the publisher and may be located using a search engine. One thing that becomes clear as you read through these articles, and especially as you engage in your own experiments, is that hyperparameter optimization is not a problem that is ever completely solved. There's always another trick you can try to improve performance. There is a saying common among writers that books are never finished, only abandoned. The same is also true of neural network optimization. The space of hyperparameters is so large that one never really finishes optimizing. One only abandons the network to posterity. So your goal should be to develop a workflow that enables you to quickly do a pretty good job on the optimizations while leaving you the flexibility to try more detailed optimizations if that's important. The challenge of setting hyperparameters has led some people to complain that neural networks require a lot of work when compared with other machine learning techniques. I've heard many variations of the following complaint. Yes, well, a well-tuned neural network may be the best performance on the problem. On the other hand, I can try a random forest or SVM or insert your own favorite technique, and it just works. I don't have time to figure out the right neural network. Of course, from a practical point of view, it's good to have easy to apply techniques. This is particularly true when you're just getting started on a problem and it may not be obvious whether machine learning can help solve the problem at all. On the other hand, if getting optimal performance is important, then you need to try approaches that require more specialist knowledge. While it would be nice if machine learning were always easy, there is no a priori reason it should be trivially simple. Alright, I think I'm going to stop there for today. Yeah, thanks for watching. Hope this was helpful. Peace.